My goal with this video is that you will be able to understand what capacitance is, like the basics of capacitance, what a capacitor does, and then like what determines the capacitance of a capacitor. What determines it and what affects it. I'm not gonna go. I'm gonna make multiple parts to capacitance, and it's gonna help us get into circuits. So first of all, you might be asking, what is a capacitor, right? Yeah, well, what is capacitance? What is a capacitor? What are all the things I'm saying? Well, if you took a capacitor, right? If I gave you a capacitor, you would notice that there are two. It's really just two conductors. It is two conductive materials at a distance away from each other. So maybe this is a 3D view. This is literally a capacitor, right? It is two sheets separated like a distance d from each other, two conductive materials. Now from top view, it would kind of look like this, right? You have one conductive material here and another conductive material here. Okay, cool, right? Well, what is the point of this? Because if you think about it, this would be like a parallel plate kind of thing, right? A parallel plate is two conductive materials a distance away from each other. What does a capacitor do? A capacitor has the capacity to store charge. So, in what scenario would it store charge, right? Like if you think about a circuit, let's say I have a 36 volt battery, and I hook it up to a capacitor like so. So let's get a scenario like this. I'm going to kind of erase these right here. Right here is the top. I'm going to make this bigger. I want to draw the top view of the circuit of a battery. I picked 36 volts. I'm not sure why, to be honest. It doesn't matter what the voltage is of the battery. This is a battery, and when I hook the capacitor up to the battery, and maybe I said 36 volts, right? This is the positive terminal. This large side, and then this small side is a negative. And then the capacitor is marked by two equal lines, right? And then this is wiring, right? A battery does not provide charge, right? There's no charge coming out of this battery. What it is providing is a potential difference. So, essentially, in the wire, there's going to be charge. Now, what's really going on here is that the negatives on this, so there's some negatives on this side, and there's going to be some positives on this side. The negatives are repelled away from the negative side of the battery, so the negatives are going to move this way, right? You're going to get flow this way. So the negatives are going to come over here, and you're going to get negatives all the way here on this side of the plate. They have nowhere else to go here, right? Because we're going to pretend there's air separating this capacitor, and sometimes you can have insulators in between them, and we're going to talk about what that does. But we're going to pretend right now there's air or some sort of vacuum in between them. We can kind of treat air, even though air is an insulator. Let's just say it's kind of close to a vacuum. There's going to be negatives being stored on that side of the capacitor. Now, what's going to happen? Well, there's going to be positive charge that's going to be getting repelled away from this side, and eventually you're going to get positives lining up here, right? Sort of the same thinking of how positives, positives getting repelled here. Same thing of the negatives getting repelled. Now, it is okay, as Mr. Lindenberger says, it is okay to say positive charge is kind of moving. What it's not okay to say is that protons are moving, because really protons, remember, they stay in place. Electrons are the ones moving around. What's actually going on is you can think of it as now negatives on this plate are getting repelled away from the negatives on this plate, so you're left with a positive charge here. And the same thinking here, you could say positives are getting repelled away, and then by convention, we say the direction of the flow of the current, and we'll talk about current as well, but kind of that direction of flow, you could call it, we would say it's from positive to negative, because you can imagine, even though it's technically really going the other way. So eventually you would see that this thing would have stored charge. It can't go anywhere, right? Now, from this point, the charges are just there. And what I can even do is I can unhook this battery away. The charges still stay there, right? Because there's nothing causing it to move just by me removing the battery, right? Because if you think about it, even if it tried to move away, it's not going to be able to go anywhere. And they are attracted with each other. There's like that electric field in between them, right? Because remember, from Gauss's law, we said that for a parallel plate, the electric field is equal to a surface charge density over epsilon naught. So the surface charge density is going to obviously be the total Q on each plate times the area, right? And you can review Gauss's law for that. So that is what a capacitor does. It just stores charge. And like I said, I could take away the battery, the charge still stays there, nothing causing it to move, and I could maybe hook up a light bulb. I don't know. That's something people do. I could hook up a light bulb, and now when I hook up the light bulb, because of this charge, it would start to light up, right? Because now this charge can kind of power, and I'm saying power, not in terms of power. I haven't really fully gotten to circuits yet, but it'll start to power the light bulb. So, and light it up, I should say. And then maybe this charge would start going away. Because the negatives want to kind of go away from each other. So that is capacitance, or that is what a capacitor does. It stores charge. Now how do we model the capacitance of a capacitor? The capacity to storage charge. So the capacitance. I'm repeating myself a lot just because I don't really plan these videos out, but I just want to make sure I know what I'm saying. The capacitance of a capacitor, like I said, is the capacity of it to store charge. And we say that the capacitance of a capacitor is equal to Q over V. So C is equal to Q over V. Now Q is in coulombs and V is in volts. So the unit of capacitance would be coulombs over volts. Now coulombs over volts, we don't always like saying, this thing has 10 coulombs per volts of capacitance. So usually we say, there's shoe boxes here that's throwing me off. Usually we would say this is a farad, named after Michael Faraday. Or I think some people say, I don't know how to pronounce it. I say farad because it's just Faraday, but I don't say the day, so it's just farad. So wait, let me explain each variable, right? What is a Q, what is a V? Well, if we have our capacitor here, there is going to be a certain amount of charge on each parallel plate of the capacitor. Now, it doesn't have to be a parallel plate. It could be like I don't know, it could be something like this and this, right? Hooked up to a battery. But I'm just using a parallel plate because we're kind of familiar with it at this point. On the parallel plate, there's going to be a certain amount of charge per plate here. And one thing to note is that they have the same amount of charge, because for every negative that goes on to here, one negative is going to kind of go away. So for every negative deposited here, one negative is going to go away. You get left with the same amount of positive charge. There's the same amount of positive and negative charge on each plate, right? And you can even imagine if there is going to kind of be one less charge here, right? There's going to be a lot of, like, there's going to be one extra positive charge kind of, having that electric force of attraction, and there's going to be one negative to kind of fill in that shoe so that each of the electric field lines kind of match up there. So if I draw this kind of bigger, there's going to be a certain amount of charge on each plate. We say Q is the charge on each plate. So when we say, when we say Q, we don't mean net charge, because that would mean 0. But we mean the charge on each plate. So let me just draw in this again, but better. So Q is a charge on each plate. So maybe there's 6 coulombs of charge here, negative 6 coulombs of charge there. V is the electric potential between them. So obviously there's going to be a potential difference created here, right? because you could think of this as, I don't know, 35 volts is negative 35 volts. There is 70 volts of electric of electric potential difference. We call it the voltage between the two plates. And if it's hooked up to a battery, this electric potential difference is equal to the voltage of the battery, right? Because the battery tries to provide a potential difference to the parallel plates of exactly that amount. Now, if you have multiple parallel plates here, the total voltage going across that of that it gets a bit more different. You have to think about loop rule, and then we'll talk about like if there are multiple capacitors and resistors and all that kind of stuff. For one capacitor, though, you would imagine that it would have the same voltage as the battery. So that is what we mean by Q over V. You would think that increasing the amount of charge on the plate would increase the capacitance, but if you increase the amount of charge on the plate, there would be more voltage, right? Because voltage is equal to the electric field times D. If you increase the amount of Q, you're increasing the amount of electric field, so you're also increasing the amount of voltage. So the capacitance doesn't depend on the amount of charge. It's not like that, right? I don't know what I'm saying. It's not like increasing Q increases capacitance. It's a ratio. Capacitance is defined as the ratio of Q over V. If I had the same 36 volt battery hooked up to a capacitor, if this has more capacitance, that is telling me that for the same voltage, the same 36 volt battery, I will get to store more charge. It has the capacity to store more charge. If you think about it, if you were to graph the amount of charge on the capacitor as a voltage, maybe as you start increasing the voltage, you're increasing the Q at a linear amount, and that slope, Q over V, is the capacitance, right? So, if you get more voltage, you get more Q, you have the same capacitance because it's the amount to store the same charge for that certain voltage. Because obviously, if you have the same capacitor and you hook it up to a 100 volt battery, you're going to get more charge, right? Because there's more voltage, but that doesn't mean that there's more capacitance. It's the ratio of Q over V. Now, what actually defines? Actually, I might make a part 2 on this. Okay, so this is an intro to capacitance. I know this video is kind of scatterbrained, but hopefully you can kind of get how, or you kind of understand now that at its very simple definition, capacitors just store charge. Capacitance is like kind of how much charge it can store for a certain voltage. That is the ratio of capacitance. We talked about how the amount of charge or the electric potential, increasing the amount of charge doesn't increase the capacitance. But what does increase the capacitance, we're going to talk about later. So I'm going to make a new video about that, probably right now.